Today we're going to talk about significant figures. And so in this video, we'll go through and we'll talk about significant figures that you're used to kind of in daily life. And we'll talk about what a significant figure or digit is. We'll go through a few cases without zeros, with embedded zeros, and with leading and trailing zeros. And then we'll talk about numbers which have unlimited significance, like counting numbers. We'll talk about rounding numbers off, significance of uncertainty, and then what do you do when you multiply and divide numbers and then add and subtract numbers. So let's kind of start by thinking about how we use these things in daily life. If someone says to you, how much does this ticket to Disneyland cost? Let's say they ask me this question, I would say about $100. So if I actually go and look it up on the internet, I discover that a ticket today costs $129 during the week. So was I wrong? Well, actually, I wasn't. If I said $100, you would kind of expect that an acceptable range would be anywhere from $50 to $150 because I was just giving you a rough number and I said $100. If, on the other hand, I had said it cost $130, then you would have a reasonable expectation that I'd be good to two significant digits. And that would mean that I would be good in the range from $125 to $135. On the other hand, if I told you that if I had said $129, then you'd pretty much figure I knew it down to within a dollar, or it could be $129.25, sure, but you would expect that it would have a range between $128.50 and $129.50 because I told you it was $129. And so this is the kind of thing in everyday life we're kind of used to. If, for example, if I had said $129.00 and I wrote that down, then you would know that I'd looked it up and I knew it to the penny. The same is true in our regular life with time. If I said, for example, a train was leaving at 3 o'clock, you might know it leaves around 3 o'clock. But if I told you it leaves at 3:12, the assumption is that I've looked it up and I know that time to a precision of plus or minus a minute. Okay, so what is a significant digit? Well, every non-zero digit is significant. So in these examples I'm showing here, in each case there are three significant digits or three significant figures. So when you look here at 24.7 meters, each of these numbers is significant. In the case here of the second case, of 0.0743, there are also three significant digits because there are three non-zero numbers, 743. In the case of 714 meters, again, we have three significant figures. Zeros appearing between digits which are non-zero are significant. So these are called sandwich zeros. So for example, in each of these cases, there are four significant figures. So in the case 5002, because these two zeros are sandwiched between two non-zero digits, they are significant. So we have 5, 1, so we have 5 at 002, all of those are significant. Same with the next number, 9.05085 meters. There are four significant digits, and the same with the number below it, 30.15 meters. All of these digits are significant because the zeros are sandwiched between non-zero numbers. Now, leading zeros are never significant. So if I write the number 0.03, I have one significant figure. That's what my SF means here, one significant figure. And you can see in bold the two numbers that are not significant and the underlined number is. So we have one significant figure. Trailing zeros following a non-zero digit are only significant if there's a decimal point. So this sounds complicated, but it's not. So look at the examples. If I take the number 0.00500, then the first three zeros here are not significant. But the next digit is obviously a non-zero number and it's significant, but the two digits after it are significant because they're zeros following a decimal point and a digit. So for example, if I wrote this in scientific notation, I would write this as 5.00 times 10 to the minus 3, where I indicate that I have three digits of significance. Take another example. Here, if I write 0.03 040, the trailing zero after the decimal point tells me that the last digit is significant. So in this case, there are 4 significant figures. Here again, I have 2.30 times 10 to the minus 5. What I get here is 3 significant digits because the trailing zero is following a decimal point. Same here with 4 significant figures, and in this case, you can see there are 6 significant figures in the 100.000. So it's 1, 2, 3, 4, 5, 6 significant figures. On the other hand, if I wrote just the number 1,000, there would only be 1 significant digit because we don't have a decimal point and trailing digits are never significant. Trailing zeros are never significant unless there's a decimal point. Okay, so a rule that we're going to talk about a little bit later in this video is what you do when you multiply or divide 2 numbers. But the bottom line is that when you multiply or divide 2 numbers, the result has as many significant figures as the number with the least number of significant figures. So let me give you an example. If I take 4.056 times 3.2 and I put it in my calculator, I get 12.9792. Now, the result only has 2 significant figures because 3.2, which is the number with the least significant figures, only has 2 significant figures. So my result has to only have 2 significant figures. So how do I do that? So we need to round this number off to 2 significant figures. So round a number off, what you do is, most of you sort of know how to round a number off, but let me just quantify it. You count the number of significant figures from the left, in this case 2, which is the 1 and the 2, or 1, 2 here, and those would be significant. But then you have to round off by using the next digit. So we look at the next digit and we use the following little mnemonic. It sounds silly, but you can remember it. 4 and below, we let it go. 5 and above, we give it a shove. So in this case, our next digit is the number 9, which is above 5. So we use this to round 12.9 to 13, and 13 is our answer. Now, take another example. 9.234 is rounded to 3 significant digits. We would take the 9, the 2, and the 3, 9, 2, and 3, and those would be our 3 significant digits, and we'd use this 4 to tell us that it's below 5, so we let it go. All right, and so our final number comes out to be 9.23. If we round off 120,323 to 4 significant digits, it comes out to be 120, 300. So this has 4 significant digits, the 1, 2, 0, and 3. The 0 because it's sandwiched between these 2 numbers. All right, so let's talk about significance of uncertainty. So let's take a look at this picture here. And if we use this ruler up here, and we use the top ruler to measure the width of this dark gray area on the screen here. So what we do is we look at this thing and we measure it, and we find that the length is between 4 and 5 centimeters. So we know it's certainly past 4 and it's less than 5. So we know that the distance can be estimated, and we can actually look at this and guess that it looks like around 4.3. So if we estimate that, what we know is that both of the digits are significant. The 4 and the 3 are both significant. The first digit is certain, and the second digit, because we kind of guessed, is our estimate, but they're both significant digits. So we would write this down as 4.3 plus or minus 0.1. And the 0.1 would be because we couldn't guess, we had to guess on this last digit. Now, if we do the same problem using the ruler on the bottom, then we're going to get something different. If we blow this up a little bit, which we can do on our computer, and we look closely, we can see that our number is something like 4.12 and 2 point something. And if I were to estimate that, I would say it's probably 2.6. So we can say that it's certainly between 4.2 and 4.3 with absolute certainty. And our next digit would have to be estimated. And if we write that down, we could write it down as 4.26. Now, all 3 of these digits would be significant. The first two are certain and the last digit is uncertain. So we would write this down as 4.26 plus or minus 0.01, whereas all these digits are significant, but the last digit here is telling us our uncertainty. So in general, when you're using an instrument, the last digit is always uncertain. Some cases, the last digit, more than the last digit, can be uncertain. Like if you're using a meter, you can look up the range of sensitivity. But in general, we assume that digital devices are good to their last digit you can read out. And it's a significant digit. The last digit is significant even though it's uncertain. And so then, just to point out, the number of significant digits can vary for the same device. If, for example, I measure with a stopwatch a time of 0.52 seconds, I have two significant figures. But if I'm measuring a longer time and I measure something that's 15.48 seconds, I have four significant figures because all of the digits in the time are significant. Sometimes we find our uncertainty, though, by calculation. You'll do this in some of the labs by taking the standard deviation, for example. So if we take a series of measurements and we take the standard deviation, we might calculate that the sigma, the standard deviation of our measurements, is, for the stopwatch, is 0.14352 seconds. And we get this number out of the calculation in our spreadsheet, and we go, great. So now we know our uncertainty, but what's clear is that we don't know our uncertainty to 5 significant digits. At best, we know our uncertainty to of the order of the uncertainty. So in this case, we would write that we would know our time, let's say the 15.48, to plus or minus 0.1 second, or because of the special case, which I'll tell you about, 15.4 plus or 0.48 plus or minus 0.14. Now, why would I include the 0.14? If the first two digits are uncertain, if the first digit of our uncertainty is a 1, we often include the second digit because it's a big fractional difference. So the difference between 0.1 and 0.14 is 40%. So if we know our uncertainty a little better than 1, we might include it. But if our number was, let's say, 2, then our 0.4 would only be 20%, and we wouldn't bother to include it. Okay, so some numbers have unlimited significant figures. There are two situations in which numbers have an unlimited number of significant figures, and that's if they're counting or equivalents. For example, if we count the number of students in our classroom and it's 23 people, we know that number precisely. So there is no limit to the significance of that number. It is 23.000 as far as we want it to go. And so it doesn't limit the precision of our calculation. If we're using it in multiplication, it's never the number which has the smallest number of significant figures. The second situation involves those where you have a conversion of a measurement unit. For example, if I tell you that there are 60 minutes in an hour, it's by definition of what an hour is. So again, that does not have a number of significant figures. It's an unlimited number of significant figures. 100 centimeters in a meter, same thing. Okay, so let's go back to our rules for math operations. We already talked about this one. Multiplying or dividing two numbers, the result has as many significant figures as the number with the least number of significant figures. So this was the example we did before, where we multiplied these two numbers together and we got something out of our calculator that had lots of digits in it. But since the 3.2 only has two significant figures, we had to round our result to two significant figures, and we got 13. If we did a division, what we would find is if we divide the same numbers, 4.056 divided by 3.2, we get 1.2675. So again, we only have two significant figures, and we would use the rounding rule to say this is 1.2, and 6 is 5 or bigger, so we round this number up to 3, so we write down 1.3. Addition and subtraction is a little bit different. And the number should be rounded to the same number of decimal places, not digits, as the measurement with the least number of decimal places. So, example, if I have three numbers that I'm taking measurements, and I'm adding the sum of them, 12.52 meters, 349 meters, and 8.24 meters, If I add them up, I get 369.76 meters. Now, the number with the least number of decimal places is the 349. So I know this only has one decimal place, so our answer should only have one decimal place. So we round this number 369.76 to 369.8 meters. So that is our lesson on significant figures. I hope this was useful.